We're ready to start. The last
Okay, so thank you. So I think we should start by thanking all the main course speakers, the organizers, and Ruth for everything for this week. Thank you very much. I'm Atelier. Yes. Yes. So now I will talk about Helly et réseau. Oh, wait. It will be more clear in English, right? Okay. So here's why you should learn French. Okay, so what is a lattice, by which I mean a poset lattice, treillis in French? I think in German, the two names are different as well. Lattice is a poset, a partially ordered set, such that any two elements x, y in P have a meet, which is denoted by x meet y, which is a maximal lower bound, and a join denoted x wedge y, which is a minimal upper bound. Okay, so you will see how this is related to injective metric spaces and Helly graphs in a minute, but what's maybe the easiest example of this? Well, you could take z to the n with the order when you ask that each coordinate is smaller than the other one, xi smaller than yi. This is a lattice. Okay? And so I will consider a lattice. I need slightly more than this assumption. I need that any subset with an upper bound has a join. It's usually the case in most interesting cases, such that every upperly bounded subset has a join. And that's my first ingredient. And now I need another ingredient, which is an action of a one parameter subgroup. So consider a cofinal action. I will define this right there. Action of H, which is either Z or R on L. So what does it mean, cofinal? It means that whenever I use this one parameter family, I can compare any two elements. It means that for every X and Y in my lattice L, there exists a positive time such that X is smaller than Y plus T. So I choose this simpler notation than writing phi T of Y. It's clear from the context, it will always be a very simple diagonal action. Then just with this data, a lattice, a cofinal action, I can define a quantity which will be a metric, the distance between X and Y, to be the infimum of all such T, such that Y minus T is smaller than X, which is smaller than Y plus T. Okay, and what can we say about this quantity? Well, there are two cases. If H is equal to R, then this is injective. And if H is equal to Z, then LD is the vertex set of the Helly graph. Okay, so it's a very, very simple recipe to build plenty of injective spaces and Helly graphs. And in fact, almost all examples I know can be traced back to, well, can be interpreted using this result, except the one using hierarchically hyperbolic groups. But this is very useful. So let me just start with just one example, a very simple example to understand what's going on here. So if I take this same example with just Z2, with the action of z acting on z2 by x1, x2 plus t is equal to x1 plus t, x2 plus t. Okay. Then what is the distance you get from just from this action of z, which is h on z2? It is the L infinity distance. Okay. And if you look at this, if you consider the graph with vertex at z2 and with an edge whenever two vertices are distance at most one, it gives you this the standard Helly graph on z2. So if I have, for instance, here x1, x2, here I have x1 plus 1, x2 plus 1, and here x1 minus 1, x2 minus 1. And you can look at the shape of the one ball around x1, x2. So here you get the Helly graph, which was obtained by thickening each square. You could also do it with R2 with the same order, with the action of R2 by the same formula. It will give you the natural L infinity metric on R2. Okay. And one natural question when you see this is that here it looks that if I just restrict to Z, I get a stronger result. Having a Helly graph instead of just an injective metric space looks better. But if you take any injective metric space, you can transform it into a Helly graph by declaring that any point at distance at most one is adjacent. So in fact, if you do that, you will get a huge Helly graph, which is not locally finite. So depending on the cases, it's better either to work with the R setup, where your space might be finite dimensional, or in the Helly case, where your graph might be locally finite. Okay, so depending on the setup, it's more natural to look at one thing or the other. Okay, so what's the nicest application of this to the case of R is the application to GLN-R. So the other kind of lattices, which are réseaux. Okay, so why am I saying GLN-R? Most often we talk about SLN-R, and the geometry of SLN-R is closely related to the symmetric space X0 of SLN-R, which is the quotient of SLN-R by its maximal compact subgroup SON, which is called the symmetric space. Okay, it's a beautiful cat-0 manifold, and on which SLN-R acts transitively by isometries. And of course, when n is equal to 2, it's just the hyperbolic plane, the real hyperbolic plane. Okay, so it's the most concrete one. So what are other models of this space? So if you just look at this, SLN-R, for instance, act transitively on basis of well, up to determinant one, but on basis of the plane. But you can look at the action on the set of, say, of all norms. So X0 will be also the set of all norms, sorry, Euclidean norms on Rn. But you need that the volume of the unit ball is 1 with volume 1 unit ball. Okay, why is that? Because you can act on the standard ball, and the stabilizer of the standard ball is SON. Okay, and this space can also be described just by looking at the unit balls. So it's the set of all symmetric volume 1 ellipsoids in Rn. When I say symmetric, I meant symmetric with respect to the origin, right? Maybe you know that the hyperbolic plane can be described as the set of volume 1 ellipses in the plane. So why am I talking about this? Well, here I want to use this result, but I want a poset. But there's no obvious relation or order relation between this, because since two ellipsoids have volume 1, they cannot be included in one another. So this is why I want to take not the symmetric space of SLN, but rather this of GLN. I will take X GLN R mod ON, which is nothing more than the direct product with R. Okay, so in case n is equal to 2, this is just H2 times R. Okay, it looks a bit silly, but it turns out that it's quite relevant. Okay, so now what do I obtain as descriptions here? I remove the normalization that the volume should be equal to 1. X is the set of all Euclidean norms on Rn. It's also the set of all symmetric ellipsoids in Rn. Okay. So why is this interesting? Because in either model, I have a natural order. So there's a partial order on X. Say if C and C prime in Rn are ellipsoids, we can say that C is less than C prime if C is contained in C prime. Okay. And if you consider these ellipsoids are as unit balls of norms, it corresponds to this norm being larger than this norm. It goes the other way. Okay, so there's a natural order relation. Right? Is it a lattice? What do you think? Take the set of all ellipses in the plane. Is it a lattice? We think not so sure. So what would it mean? So if you take, say, one ellipse here and another ellipse here, okay, I'm looking for, say, a meet. What would it be? It would be an ellipse which is contained in both, and which contains any ellipse contained in both. I could try, for instance, say this one. I could also try this one. Okay, but these two, there's no best ellipse, because I would need an ellipse containing the intersection of C and C prime. So it's not a lattice. Here I see that I have two lower bounds which do not have a common upper bound. Okay, so X is not a lattice. So what should we do? Well, instead of looking at only ellipses, we will consider all convex bodies. So I will look at X hat, which is the space of all norms on Rn, which is the space of all symmetric convex bodies in Rn. And now it has the same order relation. And now X hat is a lattice. It's quite easy to see. Why? Because if C and C prime are convex, well, what is the meet of C and C prime? It's simply the intersection. And what is the join of C and C prime is the convex hull of the union. So we have a very natural lattice associated to the action of GLN-R. And GLN-R, of course, acts by order preserving transformation of the lattice. So what we need is some nice action of a one parameter family. Well, it will just be the scaling action. So the action on X hat is by the action which I denote additively here would just be exponential t times c, the scaling. And now the distance d between C and C prime, what is it explicitly? Is the infimum of all positive t, such that exponential minus t c prime is contained in C, which is contained in exponential t c prime. Okay. And what this result tells us, this space with the metric D is injective. Okay, so already it's quite nice. And we would like to relate it to the group we started with, which is GLNR. So we have a natural action and of GLNR, it is by isometries, simply because it commutes with the diagonal action and it preserves the order. And it's a simple remark that GLNR acts properly and co-compactly on X hat. So why is that? It's so the space of all convex bodies of Rn with the metric D, it is a proper metric space. It's not hard to see that if you allow your convex body to move only in a bounded amount inside two convex bodies, then you can always find a limiting subsequence. So it's a compact space. So you will always have a compact limit. So the main problem could be that this space X hat could be much bigger than the symmetric space we started with. Well, this is a very fun remark that if C is in X hat, so C is a convex body in Rn, we can consider the largest volume ellipsoid contained inside C. Denote the largest volume, so it's called the Juin ellipsoid in C. And one fun property of this largest volume ellipsoid is that not only do we have B contained in C, but C is also contained in square root of NB. So what does it mean? It means that if you look at the definition of the distance between B and C is smaller than the log of square root of n. But B is an ellipsoid, so B is in X, the symmetric space of GLNR, on which GLNR acts transitively on X. So GLNR acts co-boundedly on X hat. And since X hat is proper, this action is in fact co-compact. And so we get that GLNR acts properly co-compactly on an injective metric space. So one could wonder what's the relationship between this new metric space and the classical symmetric space. Well, in the classical symmetric space, you could look at metric given by flats. So it's the way to measure points inside a symmetric space, to look at flats, which are isometric copies of Rn. And the usual metric is taking the L2 metric on Rn. Well, if you take here the standard L infinity metric on Rn, and if you look at the injective hull of this space, this is exactly X hat. Okay, so the injective hull of the symmetric space with the L infinity metric is the space of all convex bodies. So by the way, I should mention that I don't know a good description of the injective hull of H2. It can be described inside the space of all convex bodies in R2. We know by long that it's at bounded distance from H2. So at bounded distance from the set of all ellipsoids of volume 1. But I don't have any description of this space. So what are nice corollaries of this fact is that if gamma, say, is a uniform lattice, is a co-compact lattice, lattice in SLNR, then up to taking the product with Z, it becomes a co-compact lattice in GLNR. It is injective. And this is essentially the only construction I know of a natural action, well, of an injective group, which is not known to be Helly. It's through this space, which is infinite dimensional, but still proper. All other constructions I know are, well, finite dimensional, and in the end, just Helly. Okay, so this is very nice if you like symmetric spaces. If you prefer building, there's another way to do it. So another corollary, that if gamma is SLNK is a co-compact lattice, where K is a non-Archimedean local field, for instance, QP, then gamma times Z is actually Helly. Why? Yes. One could hope for a very precise description. These convex bodies are exactly the one you get when you look at the injective hole of H2 inside this injective space. We know that H2 is contained inside this larger injective space of all convex bodies in R2, but it's not minimal. So what's the minimal subset? So which regularity properties should it have? Could it be described as a set of functions on the boundary of the H2? I don't know. I'm not sure it's, well, it's a very natural question. I'm not sure, I don't have any direct applications, but it's very natural. Any other question? So here I mentioned that you get that it's Helly in place of injective. It's just because that if you work in a non-Archimedean local field, the space of all ultrametric norms is much better behaved, and it's already a lattice on the spot. You don't have to take the extension to, and we don't have a nice interpretation of this space in terms of convex bodies, but rather of norms. And when you look at that, you may also wonder, what about these lattices? Are they Helly? It's open. And it's also open whether co-compact lattices in SLNR are biautomatic. So we really don't know. And another very nice remark is that such groups are very rigid groups. So for instance, they have property T, then even have a stronger version of property T. So in particular, they will not act on a Cadieux cube complex. They will not act on a hyperbolic space. So among Helly groups, you have very rigid groups, which is not the case if you look at co-compactly cubulated groups, for instance, in general. Yeah. Okay. So now I will give you another application of the result of passing from a lattice to an injective metric space or to a graph, which is through looking at geometric realizations of posets. So I will, just before stating the result, I will have two definitions, maybe two or three. Yeah. So a poset P is homogeneous if I don't want infinite change, essentially, for any comparable elements X and Y in P. There exists a bound on the length of chains in P, chains from X to Y. So this will be useful to have some discreteness properties. And also, when a poset is homogeneous, it's somewhat easier to check that the poset is a lattice or not. You just have to look for bow ties. So it's a proposition due to McClellan. So a homogeneous set P is a lattice if and sorry, or P a homogeneous poset, then the equivalence is P union 0, 1 is a lattice. I can always add an artificial minimum and maximum element to my poset if and only if P has no bow tie. So what does it mean? So what is a bow tie? It looks like this, right? So we have A, B, C, D. So for all A, B smaller than C, D in P, I can find a middle element somewhere here, X. There exists some X such that A and B are smaller than X, which are smaller than C and D. It's just that if you ever had, say, 2 upper bounds, you can find a lower common upper bound. It's very natural, really. And I just need another definition, which is the notion of a flag poset. Poset. Yes. So has no bow tie. The bow tie is ABCD without a central point. With an X in the middle, without X in the middle would be a bow tie. Yeah. The other question. So poset P is not the flag. Or any pairwise X, Y. For geometric conditions, that locally is a flag lattice. So what does it mean? That for all X in P, I look at the third poset consisting of elements which are above X. So I ask that this is an upper flag poset without bow ties. So assuming that it doesn't have bow ties, it's the same as asking that it is a neat semi-lattice. But in fact, it's sufficient to look at this condition having no bow tie. And the symmetric condition for X, P smaller than X, is lower flag without bow ties. Okay, so the symmetric definition, any 3 elements which are pairwise lowerly bounded have a common lower bound. So what's the conclusion then? Then the L infinity orthoscheme realization is locally injective. And in fact, it's an equivalent characterization. If it happens that the L infinity orthoscheme realization is locally injective, it means that you must have these properties. So this result should be thought as, in the world of L infinity orthoscheme metrics, as the link condition, right? You just have to check locally a link condition. And here, the link condition will be essentially the flag condition. So I will make this more precise just by giving the example of a Cat-Zero cube complex. So if X is a Cat-Zero cube complex, and well, finite dimensional, because you want that it's homogeneous, Y, I will take P, the poset of all cubes of X. Okay, it's a poset for inclusion. Then I will check that these conditions hold. So for any cube, say K cube Q in X. So what is I will start with this one, it's easier. The poset of all cubes contained in Q is the Boolean poset 0, 1 to the K. it's a cube, the set of subcubes of a cube. Okay. So in particular, the Boolean poset, it's a lattice and it's lower flag. So there's and now what's the other one? The set of cubes in X containing a given cube. So the fact that it's so we want to check that it's upper flag without bow ties. So this is the same. Upper flag is the same as the flag condition for cube complexes. And without bow tie is the same as asking that the link is simplicial. Okay, you don't have two squares adjacent to the same two edges, for instance, in a given vertex. And so, in particular, this result tells you that the L infinity metric on a Kadziaow cube complex, well, up to a factor 2, it's isometric to the geometric realization of the poset of all cubes. It is locally injective. And since X is simply connected, we have seen using the global to result for injective spaces that X, the infinity, is injective. So it applies very nicely for Kadziaow cube complexes, but it is more general because you are allowed to fold along a given a diagonal edge of a square, for instance. Another example is that if X is a Helly graph, then the poset, which I denoted yesterday, Px, of all round cliques of X. So round cliques are cliques which are intersections of balls. This is natural poset for inclusion. It satisfies the properties if you assume some finite dimensionality condition on the Helly graph to have the homogeneous property. So this result is a way to see that if you take a Helly graph, take this poset, take the geometric realization, it will be locally injective. So it will be injective without knowing that it's the injective hull. It's a purely combinatorial way to see that this is actually injective. Okay, any questions? And one very nice application of this fairly general result is for braid groups. So I will say just a few words about this, giving a little bit of echo to Ruth's talk. So why braid groups? Because braid groups have a natural lattice structure, which is called a Garside structure. So in order to make it as simple as possible, I will just take the 3-strand braid group. Okay, so B3 has 2 generators, S1 and S2, and one relation S1, S2, S1 is equal to S2, S1, S2. Okay. And inside the 3-strand braid group, you have a very nice semi-group, which is the positive monoid, which is a set of positive braids, the set of words written in positive powers of S1 and S2. In terms of braids, this corresponds to the fact that whenever you have a crossing, the left strand always goes above the right strand. Okay? And then there are partial orders on the braid group. There are, in fact, 2 orders. The left order, we say that a braid is left smaller than another one. If it is a prefix, if there exists a positive braid P, such that GP is equal to H, it's called left because it's left invariant under translation. And there, the other one, the right order, if there exists a P, such that PG is equal to H. And why are these orders important? It's because of the following result of Garside. So the first one is that B3 with either order, say the left order, is a lattice. And the second one is that, I need another element, which is delta, which is S1, S2, S1, which is the Garside element. So he remarked that the set of all positive braids, which are prefixes of the Garside element, coincide with the set of positive braids, which are suffixes of the Garside element. And this is quite powerful, because here the prefixes are S1, S1, S2, and S1, S2, S1, but S1, S2, thanks to this relation, it's also a suffix. And using just this property and using conjugation by delta, you can show that this action, so for all braid, there exists a power such that when I multiply G on the on the left, say, by delta, it becomes positive. Okay. When I write my element, I can, if I take n positive enough, you would say, it becomes a positive braid. So what does it mean? It means that the action of the subgroup generated by delta on this poset is cofinal. Given any two braids, up to applying the Garside element, I can compare the two braids because the difference between the two braids will be positive. So from the result I stated, we deduced that, in fact, B3 with the associated distance D is a Helly graph. But what is this? This can be made much more explicit. Here, it's just a Helly graph. The Helly graph of B3 with respect to this generating set, this finite generating set. So as a consequence, we see that B3 is a Helly group. And this argument works more generally for all braid groups, more generally for all finite type Artin groups, and even more generally for what are called Garside groups, which are lattices with a Garside element, which have the same combinatorial properties. And this result is due to Juin and Ozaida, that Garside groups are Helly. Yeah. And in fact, there are two nice objects that you can get out of this. One is the Helly graph, and the other one is an injective metric space, which will be here just a simplicial complex. So let X denote the simplicial complex with vertex set B3 and whose K simplices are chains in this order, G0 left smaller than G1, left smaller than Gk, but not infinite, which are between G0 and G0 delta. So it's a simplicial complex, and every simplex is a chain, so it has a natural order. We can look at the geometric L-infinity orthoscheme realization of it. Then this orthoscheme realization with the L-infinity metric is injective. So why are they interesting? I can try to draw a picture. So if I just try to draw the geometric realization of sigma, what would it be? So here I have my delta, here the identity, and I have two chains, two ways of writing delta, S1, S1, S2, and here the other one is S2, S2, S1. So this geometric realization locally looks like this, the union of two simplices along this diagonal edge. And in fact, X will be the product of a tree of triangles by R, whereas the Helly graph here will just be the Helly graph, which is obtained by taking this graph and adding edges. So you need to add edges to make it Helly. Take a thickening of this injective simplicial complex to make it a Helly graph. And depending on your taste, it could be more interesting to have one structure or the other one. And this applies also to locally infinite case, like the Artin complex, for which the Helly graph is locally infinite, but the underlying injective metric space is finite dimensional. And what's very fun is that if you take this complex, okay, and instead of L infinity, you put the L2 metric, it is conjectured to be K0. Not with this Garside structure, it's false, but with another Garside structure, there are two Garside structures. So it's the most advanced way to prove that braid groups are K0, which is replacing the infinity by a 2 here. So it's open. But with L infinity, it works magnificently, I think. That's all. Thank you very much.
No,
Thank you.
Yeah,
thank you.
weekend.
Thank you.